All right, so this question is all about essentially looking into the safety features of a car and just in general why these are important for the physics of what's going on in a crash. We have, in this case, we're told the mass of the car, the mass of the crash test dummy, and the speed of the car. So let's take a look at that as an initial and final situation. So we have, in terms of the initial situation, we've got this car, which I'm just going to approximate as a rectangle. And inside the car, we've got a crash test dummy, which I'll draw in bright safety orange. And at the beginning, what do we know about their motion? Are they moving? Are they staying still? What do we know about their motion here? Yeah, they're both moving forward at the same speed, at this same 30 meters per second. So we can draw out a velocity arrow for each one of them. We can say that each one has a velocity of 30 meters per second. So the car itself has a velocity of 30 meters per second, and the crash test dummy also has a velocity of 30 meters per second. So their velocities are exactly the same. V initial car equals 30 meters per second, and V initial of the crash test dummy is also 30 meters per second. And what do we know about the final situation? Yeah, they both come to a complete stop. So the car is now at speed 0, and the crash test dummy is now also at speed 0. So V final of the car is 0 meters per second, and V final of the dummy is also 0 meters per second. Everything has come to a complete stop. And just with that information, would you say momentum has been conserved or not here? No, momentum has not been conserved, right? We start with lots of forward momentum, and we end with no momentum at all, 0 momentum. Which means what had to have happened here? What has to happen to a system in order for the total momentum to change? Yeah, there's got to be an external force. And in this case, what is that external force from? Yeah, the wall is applying a force to the system, and that force causes an impulse, force times time, that brings the whole system to 0 momentum. Because that's what an impulse is. An impulse is a force that applies for some amount of time, and that causes a change in momentum. So let's look into some of the values here. In fact, let's start by looking at the values of momentum for each of these. If we take a look at the actual momentum of each one of these, what is the initial momentum of the car? Or how would we calculate that? Yeah, we just multiply the mass, which for the car is 1,500 kilograms, times the velocity, 30 meters per second. 3 times 15 would be 45, 3 more zeros, so 45,000 kilogram meters per second would be the initial momentum of the car. And since this is a vector quantity, we should have a direction associated with that. So that will be in the same direction as the velocity itself. So the momentum of the car is 4,500 kilogram meters per second in the forward direction. And what about the momentum of the crash test dummy? If we multiply that mass, 60 kilograms, times the same velocity, 30 meters per second, that looks like 1,800. 1,800 kilogram meters per second. So the momentums are very different. The two objects have the same initial velocity, but they have very different initial momentums because they are different masses. So keep that in mind. If objects are moving together, they have to have the same velocity as each other, including direction, but their momentums are going to be very likely different because their masses could be different. Any questions on that so far? And what would we say about the final values of momentum? Yeah, they're both 0 because they both come to a complete stop. So 0 kilogram meters per second, which means there has been a huge change. And we can figure out that change just by subtracting. This is essentially looking for the delta column in the momentum chart. You got your initial momentum column, your final momentum column, and then you can subtract final minus initial to find the delta momentum. So if we wanted to write out the change in momentum for the car, let's say, how would you calculate delta momentum? Yeah, 0 minus 45,000. Or since we're talking about vectors, keep in mind we are not subtracting the number 0 minus the number 45,000. We are subtracting a 0 vector minus a vector that is 45,000 to the right. So if you take the 0 vector and subtract a vector that's 45,000 to the right, what would you get? Yeah, 45,000 to the left. So that means the change in momentum for the car is 45,000 kilogram meters per second to the left. In fact, we could just draw that as exact same magnitude, but opposite direction. So there's the change in momentum for the car. And then the change in momentum for the driver or dummy would be what? Yeah, 1,800 kilogram meters per second to the left. So it's experiencing a change in momentum that's exactly opposite to the momentum it started with, because that's how much you need to change to get back to 0. So that's the change in momentum. That is, I guess that's question 8 here. What's the initial momentum and the change in momentum? And of course, the final momentum for both would be 0. And question 9 is asking about impulse. What is meant by impulse here? What is impulse in this context? It's partly caused by the wall, at least one of them is. But what does impulse mean? It causes the change in momentum, yeah. And what is that? What has to happen to make that happen? What impulse is, or what do you have to do to an object to make its momentum change? Yeah, you've got to apply a force, and that force has to last for some amount of time. Impulse is specifically force times time. How much force you apply times how much time that force lasts. And we usually write that as J, and a lowercase j, and that J should have a vector sign over it because force is a vector, therefore impulse is also a vector. Because time is just a scalar. Time is just a scalar multiplier here. So if you take the amount of force that's being applied times how much time that force lasts, that tells you the impulse associated with that force. And an impulse tells you a change in momentum from that, or because of that force. But really the change in momentum of the object is the sum of all of the impulses acting on that object. So there may be several forces acting on an object, and those forces may all last for different amounts of time. If you want to find the actual change in momentum of the object, you calculate all the impulses from all the forces acting on the object and then add those impulses together as vectors. So it's not always correct to say that the impulse is the change in momentum of the object, because there might be several forces causing impulses. Any one of them doesn't necessarily cause the change in momentum, but the total of all of those impulses does cause the actual change in momentum of the object. Any questions on that so far? So in this case, presumably there's only, I think we can probably assume there's only one main force acting on the car and one main force acting on the driver or dummy. Or I guess we could just sum it up as the total force acting on the object. But what force, or what does that tell you about the amount of impulse? How much impulse is the car experiencing? Yeah. Although I would be careful about the negative there. A vector itself doesn't really have a positive sign or negative sign. A vector has a direction. So in this case, I think I would describe that as 45,000 to the left or 45,000 backwards. You could say its x component is negative 45,000 because components have positive and negative signs. But the vector itself is 45,000 and then describe a direction. Realistically, if you call it negative 45,000 and we're talking about a one-dimensional situation anyway, I think anybody would understand what you mean. But formally, a vector has a direction, not a positive or negative sign. So that 45,000 to the left could also be described as the impulse experienced by the car. And likewise, the 1800 kilogram meters per second could be described as the impulse experienced by the dummy, the total impulse. And again, I think we can assume that that impulse is basically the result of one big force applied for some amount of time during the crash. So that's the net impulse applied to each object. And do these numbers depend on the details of the crash? It's kind of ambiguous what they mean by details, but I think they mean like the stuff described in part 10, whether or not there's a seatbelt, whether or not the airbag works. So do things like a seatbelt, an airbag, the car crumpling up, do those influence these numbers we just got? And how do they influence those? Like, can a seatbelt make it so that you're not experiencing an impulse of 1800 kilogram meters per second? How did we calculate that 1800 in the first place? Like, where do we get these numbers? Yeah, that's the final momentum minus the initial momentum. Does the presence of a seatbelt or the presence of an airbag change your final momentum or your initial momentum? Yeah, the momentum, the delta momentum is still the same whether you're using a seatbelt or not. We're still assuming you start at 30 meters per second, and we're still assuming you end at 0 meters per second. That's not changed by what's going on inside the car. And I don't want to say seatbelts don't do anything. Seatbelts do an amazing thing, but what the seatbelt does is not changing what the delta momentum is. So the only way you can really limit the change in momentum, the total impulse, is by changing what the initial was or what the final was. So you could certainly have a smaller delta momentum if you were driving slower in the first place, or if you didn't come to a complete stop. But the thing is, the delta momentum itself isn't the thing that is dangerous. Delta momentum isn't what causes injuries. For instance, if you're going 30 meters per second and then come to a complete stop, notice that we haven't specified how that stop happened. Maybe that stop was from crashing into a wall, or maybe that stop was from gently applying the brakes and gradually drifting to a stop. Or maybe it was from just letting off the accelerator and gradually coasting until you eventually come to a stop due to friction and air resistance. All of those situations, whether it's a sudden stop or a gradual stop or a really, really gradual stop, those all involve going from 30 meters per second to 0 meters per second. So what's the difference between all those situations? If they all involve starting at 30 meters per second and ending at 0 meters per second, so they all involve the same change in momentum, yeah, this is all about time, how much time that process of stopping takes. A sudden crash takes a very short amount of time. gradually drifting to a stop. It's still the same overall change in momentum, but it takes more time. And this is where we get into the idea of impulse again. That impulse is the force times time. Impulse you can't do anything about other than not drive as fast in the first place. Impulse is going to be 1,800 kilogram meters per second. But if you make this process take a long amount of time, what does that tell you? If the impulse has to be 1,800, but you can make the process take a long amount of time, yeah, that's going to be a smaller amount of force. If you have force times delta time has to equal a certain impulse, a large amount of time is going to mean you have a small force. You're essentially spreading out that impact over a longer amount of time, so the force gets more spread out. On the other hand, for a very sudden stop, if delta t is very small, what does that tell you? Yeah, you get a large force. And force is really the dangerous thing here. The change in momentum doesn't really matter all that much in terms of whether this causes any injury. The important thing is the amount of force. In order to make the crash as safe as possible, you want to make the forces involved as small as possible. And to make the force small, you need the time to be large. You need the impact to take a long amount of time. Yeah.
So in the DL after, they talked about how the distance is different when the hood of the car crumples versus when the dummy flies out of the car. So is that saying that like when the distance is increasing, then the time is decreasing, and that's why the force is so much higher when you're flying out of the car? I was a little confused.
It's not really so much about distance, it's about the time it takes to go from the speed you start at to a complete stop. For instance, a lot of this really depends on what object or what situation is providing that force. Like for instance, the car is coming to a complete stop because it's experiencing a force from what other object? Yeah, the wall is applying a force to the car. And so the impulse on the car is caused by the wall. So the 45,000 kilogram meters per second to the left impulse on the car is caused by a force from the wall on the car. But the impulse on the dummy, what's the force on the dummy itself? Or what's causing that force? Yeah, the seatbelt, or if there is no seatbelt, then presumably maybe the dashboard or an airbag, whatever the crash test dummy bumps into, caused by presumably whatever part of the car it hits. And so that's still going to be a force on the dummy, but it's going to be a force from some other object that it impacts. And note that this impulse, the 1,800 kilogram meters per second, that's not directly caused by a force from the wall, because the wall is not exerting a force on the dummy, unless, again, if the dummy flies through the windshield and crashes into the wall anyway. But the force on the dummy is going to be caused by whatever the dummy actually bumps into. And so if that's talking about the seatbelt, well, let's say there is no safety features at all. If the dummy just flies forward and crashes into the front of the car at high speed, what would you say? What would you expect about the amount of time that impact takes? Yeah, that'll be very fast, a very, very sudden, short amount of time. So since that's a very short amount of time, that means it's going to involve a very large force. And that's what the dangerous thing is. But if there's a seatbelt or an airbag, or if the front of the car crumples up, like if you're talking about the car smacking into the wall and not crumpling at all, that's a very sudden stop. But if the car is crashing into the wall and crumples up, if the front of the car is a little bit softer and is able to crumple, that impact takes a little bit more time. So that's really what this whole crumple zone thing is all about. If you have a section in the front of the car that is able to crumple up, it's not built really solidly. And again, kind of like a circuit breaker or a fuse in some ways, this is a deliberate weak point built into the design so that it will fall apart predictably and safely. In this case, though, that deliberate crumpling is so that the impact takes more time. And taking more time means that there's going to be less force involved and less likely to lead to serious injury. So all three of these safety features are really all about making the crash take more time, making that sudden impact take more time and therefore involve less force. So it's not exactly about distance. I mean, the objects are traveling forward as they are continuing to travel forward as they slow down until they come to a complete stop. But it's really more about time, force times time. Because if you multiply force times distance instead, what do we get if you multiply force times distance? Do you remember seeing that in 7a? If you multiply force times distance, what are you doing? You apply a force on a moving object as it travels some distance. What does that count as? Acceleration is how fast the velocity is changing. But force times distance, yeah, exactly, that's work, which is a change in energy. So multiplying force times the distance traveled is very useful if you're talking about energy changes, including kinetic energy. But in this case, we're not looking at energy, we're looking at momentum. So that would involve impulse, which is force times time. And of course, these are both happening. You're applying a force to the object as time passes and also as the object moves some distance. So that force you're applying is changing momentum and changing the kinetic energy. But which one you actually care about determines whether you want to multiply force times time to figure out the impulse or change in momentum, or multiply force times distance to figure out the work or change in energy. So these are very similarly structured formulas in some ways, but they're subtly different in the sense of, are you looking at momentum changes or energy changes? As for the seatbelt and how that increases time, if there is no seatbelt, then the dummy presumably crashes right into the dashboard, and that's a very sudden stop because you're going at the full 30 meters per second until you hit the dashboard, and then there's only a very short amount of time to come to a complete stop. But with the seatbelt gradually slows you down over the course of that entire process. So the seatbelt, since it's a gradual slowing down, instead of going at full speed and then coming to a sudden stop, you are slowing down throughout that entire process of moving forward. That means that the seatbelt is taking more time to slow you down and bring you to a complete stop than the dashboard would. Same thing with an airbag. If you crash straight into the dashboard, that's a very sudden stop. But if the airbag inflates, you are now pushing through this inflatable pillow, and you're going to be taking more time once again to come to a complete stop. A more gradual force, a smaller force over a longer period of time. And in some ways, you can even see this not only in car design, but even in road design. Like if you're talking about let's say a section of highway where there's 2 lanes that merge together, you may have seen this on highways. If you have, let's say, like 2 lanes coming in and merging together. And maybe there's like a concrete pillar there or something. You don't want to risk people veering off the road and crashing into the concrete pillar. So what do they usually put in this area leading up to that concrete pillar? Have you seen this on roads where you've got like 2 roads coming together? Yeah, you've got these sand things, right? These like bright yellow plastic barrels full of sand or sometimes full of water. These safety orange or safety yellow plastic barrels full of sand or water. That way, if you crash into it, instead of crashing into the concrete pillar and coming to a sudden stop, you plow through these sand barrels, and the sand barrels don't instantly stop you. You smash through them, but they're going to slow you down more gradually. Every extra bit of time it takes to slow you down means more time and therefore less force and less danger of serious injury or death. So all of these safety features, basically any safety feature other than the ones that are trying to prevent the crash in the first place, all the safety features that kick in after or during the crash are all about stretching out that amount of time to limit the force involved. And this isn't even necessarily noticeable while you're watching a crash. If you're looking at this, the seatbelt or the airbag or the crumple zone might make a difference between like a 1/10 of a second versus a 1/100th of a second. And those are both over in a flash. You don't really even notice visually that they are different amounts of time. But the difference between a 1/100th of a second versus a 1/10 of a second, that's 10 times as much time and therefore 1/10 as much force. And that could make the difference between life and death in a lot of situations. So that's really the big message of all of these safety features. It's all about stretching out the amount of time the impact takes and therefore reducing the amount of force that's involved. Still the same overall impulse, but more time means less force. Any other questions on that one? Cool. Let's try out another example of a momentum chart in more detail then. Let me see if I can pull up one more example. Can you see this one? Example with the dog catching the ball. Let's look into this one, because this one gives us a lot of information about a certain situation, and we want to figure out some more of the information. Here we have this thrown ball, and we know its initial velocity is purely in the x direction, but it doesn't tell us how fast it's going. In fact, that's one of the problems, one of the questions it's asking. What's the initial velocity of the ball? So it might be useful here to list out the unknowns. In fact, I think it's often a good idea to, while you're working through a problem, list out what you know and what you're trying to find. So a quick skim through the problem, figure out what situation it's describing. And sometimes it's useful to just skim through that and then look ahead at what's it actually asking for. In this case, we're looking for what's the final velocity of the ball and what's the initial velocity of the ball. So these are the unknowns here. We don't know the final velocity of the ball, though it looks like we do know the angle, the direction. But we don't know how fast it's going at the end, and we don't know how fast it was going at the beginning. So those look like they're going to be our big unknowns. But looking over what's going on here, we've got the initial situation illustrated here. We've got the dog leaping into the air at 60 degrees. And also we know the dog's velocity, 12 meters per second at that 60-degree angle. So let's start labeling these. We know the initial velocity of the dog. Is 60 degrees, 60-degree angle, and 12 meters per second. So speed of Jersey the dog initial is 12 meters per second at this 60-degree angle. 60 degrees from horizontal. Which means we should be able to split that into components, right? How would you find the x and y components of this? Like if we wanted to find, yeah, we should be able to use sine for the y component. because the y component, as long as you're using the angle it makes with the angle the vector makes with the horizontal, the y component will always be opposite to that. So the y component will always be sine. And yeah, then the x component should be 12 times cosine 60 because the x component is adjacent to the angle. And it looks like these are in the positive x direction and positive y direction, so we don't need to worry about any negatives. And if I remember correctly, cosine 60 is 1/2. So 12 times cosine 60 is 12 times 1/2. So that'll be 6. And then sine 60 is root 3 over 2. Yeah, so that just becomes 6 root 3. So that means our initial velocity of the dog can be written as 6, 6 root 3 meters per second. So that'll be the initial velocity of the dog. And how would you convert that to a momentum? Yeah, we can multiply by mass. Pythagorean theorem would allow us to find the magnitude, but we already know the magnitude, 12 meters per second. So we don't need to get back to the magnitude. But yeah, we could use the mass, which for the dog is 15 kilograms. So, and the thing is, there's two ways you can do this. You can multiply the magnitude by 15. You can multiply 12 meters per second times 15 kilograms to get the magnitude of momentum, and then split that into components. Or we could just multiply both of the components, x and y components, by 15 kilograms individually, because you're multiplying the velocity vector times the mass. That means you could multiply the magnitude by the mass and keep the angle. Or since we already split it into components, multiply each component by the mass individually. So let's go ahead and multiply the components. We know we can say the initial momentum of the dog Jersey is 6 times 15, that'll be 90. And then 6 root 3 times 15, that'll be 90 root 3 kilogram meters per second. Let's go ahead and get a decimal approximation of that though, because we're gonna have to be adding this to other values later on. So 90 root 3 is about 156. So that'll be the dog's initial momentum. 90 in the x direction, 156 in the y direction. Any questions on that so far? And as for the ball, we know the ball is moving purely in the x direction. Do we know how fast it's moving? Looks like it didn't tell us that, right? It didn't tell us how fast the ball is moving. And in fact, that's what it's asking in part B. So part B is asking for the initial velocity of the ball. So let's go ahead and treat that as an unknown. It's got some initial velocity, I'll just call that VB, but that is purely in the x direction. So that'll be VB comma 0. So even though we don't know its initial velocity, we can write its initial velocity in terms of this unknown variable VB, because we know its x component is that total VB value and its y component is 0. If it hadn't been purely in the x direction, we could, but we knew the angle, we could still use sine and cosine. We just write this as VB cosine theta and VB sine theta. And then again, how do we turn that into a momentum? Yeah, multiply by mass, which for the ball is 5 kilograms. So the initial momentum of the ball will be 5 kilograms times VB, comma 0. So we now have the initial momentum of the dog and the initial momentum of the ball in terms of this unknown variable VB. What do we know about the final situation? Yeah, the dog catches the ball, so they're both moving together. If they're both moving together, what does that tell you about the final results in terms of the actual values? What's got to be the same there? Yeah, they've got to have the same velocity. So we don't know what that velocity is, but we do know it's the same for both. And we even know the direction. It's got a direction of 30 degrees above the x-axis. So the final velocity is going to be some unknown 30 degrees above the axis vector. So that'll be v final. And it's the same v final for both. Any questions on that so far? And we could split that up again into x and y components. Based on the fact that we know the angle is 30 degrees, what does that tell us about these components? Can we write those in terms of the 30-degree angle? Yeah, the x component will be v final times cosine 30, and cosine 30 should be root 3 over 2. So that'll be v final times root 3 over 2, which is, what was that again? Root 3 over 2, 0.867, or no, 0.866. So 0.866 times v final. And then v final y, we do the same thing except using what instead? Yeah, v final times sine 30. And sine 30 is 1/2, so that'll just be v final over 2, or 0.5 v final. So that'll be, we can now write v final as, in terms of vector components, it'll be 0.866 v final, comma 0.5 v final, in terms of the components of the vector. And then we can turn that into momentums by multiplying by each one of these specifically. 15 times those components will be the dog's final momentum, and 5 times these components will be the ball's final momentum. So let's write those out as well. We can say the final momentum of the dog will be 15 times each of those. So 15 times 0.866 v final is pretty close to 13. 12.99. I'll round that off to 13 v final. And then 0.5 times 15 would just be 7.5 v final. And then same idea for the ball, just use 5 instead. So 5 times 0.866, about 4.33. And then 5 times 1/2 would be 2.5 v final. So we now have, even though we don't know all the values, we at least have expressions for the initial momentum of everything and the final momentum of everything in terms of the components. Any questions on that so far? Then let's try putting all this together with a momentum chart, because I think a momentum chart is going to be a very good way to organize the information here. Yeah, I can actually grab everything. Let me tidy this up a little bit. I'm going to leave off the units because these are all going to have the same units anyway. So we've got our initial momentum for the dog. Final momentum for the dog. Final momentum for the ball. and initial momentum for the ball. And of course, we can draw these in as arrows also, but we don't really need the arrows for the calculations. I would certainly recommend drawing in the arrows like 90, 156. That'll be a little bit to the right and almost twice as much up. So I would definitely recommend drawing in the arrows. But it can be kind of difficult to draw in the arrows until we know these values, so we know the relative sizes. But if we add these up, we can fill in total, for instance. We just add 90 plus, this is the x components, 90 plus 5 VB. And again, I'm leaving out the units here because we know it's all going to work out to kilogram meters per second anyway. And then 156 plus 0. So that's the total initial momentum. Wait, 156. Total initial momentum. And then final initial momentum, we can just add these up, again, one component at a time, and combine like terms. 13 plus 4.33 would be 17.33 V final, and 7.5 plus 10 or plus 2.5 would be 10 V final. So we have initial total momentum, we have final total momentum written in terms of some unknowns. What should we expect the change to be, though, the total change? If we're looking at from right before the dog catches the ball to right after the dog catches the ball. So the dog and the ball are interacting with each other, but there's not really enough time for any other forces to play a major role. So what would you expect the total change to be? With no external forces, what should you assume about the total momentum? Yeah, zero change. The only way you can change the total momentum is external forces. And there is technically an external force here. There's gravity acting on both of them. But gravity is a fairly weak force compared to the impact force of the dog's mouth on the ball. So I think we can ignore that since that's not really a very strong force compared to the other forces involved. So let's assume that this is a closed system. We've got zero total change in momentum. In that case, what does that tell you about the initial total momentum and the final total momentum? Yeah, they're the same. We can set these equal to each other. And this is one of the big advantages of splitting into components. We can do this one component at a time. We can set the x components equal to each other. And note that this has two unknowns. We don't know the initial velocity of the ball, and we don't know final velocity of the system. But the other equation, 156, the y component, initial y component equals final y component, 10 v final. This has only one unknown. So we can solve for that unknown. And what would we get there? If we want to isolate v final, we can just divide by 10, right? Divide both sides by 10, we get 15.6. So that actually tells us the final velocity of the system. Both the dog and the ball are moving together at 15.6 meters per second in the 30-degree direction. And with that number, now that we know the final velocity, the value of v final, what can we now do with that value? Yeah, we can plug that back into the other equation because we had another equation that had two unknowns, v final and v initial ball. But now that we know v final, we can plug that in here, replace v final with 15.6, multiply that out, and then solve for v ball. So that'll tell us how fast the ball was going at the beginning. And then with that information, you could actually fill in those numbers in the momentum chart, calculate the changes, and even draw in the arrows as well. But that now gives us all the information about this entire collision. Any questions on that? All right, like I said, get more practice with this, get as much practice as you can, try out as many example problems as you can find, and even just make some up. If you just say, let's say you've got this rock in space with this mass and this velocity, and this rock with this mass and this velocity, and they collide, try it out. Make up some situations, draw out the momentum charts, and try to develop an intuition for what happens. Like try to develop an intuition for, well, if these objects are going at these speeds, the result is probably going to be going in this direction. Try and develop a visualization ideas for what you should expect as the result. Because it's very useful to go into this with some idea of what to expect and then run the numbers and check if the numbers match up with your expectation. So get some practice. Feel free to email me if you have any other questions, and I will see you next time. You're welcome.